Good morning. Today we discuss other issues of the operational amplifier, namely that what is the impact of output resistance and how to find the output resistance for a given application, and then how to find the input resistance of the operational amplifier. These two issues we will see in this class. If possible, we will also see something more about CMRR and some examples to go with the input resistance and output resistance. So, today our main focus would be input resistance of the op amp and what effect it has got on the design, and then the second one is the output resistance. So, these two issues we will discuss today. Now, first let us take the input resistance. Okay. Now, the input resistance is an important parameter in any instrument. Let us see why should one worry about the input resistance part. Now, for example, if I take any general instrument, for example, I will connect a voltage source, then I connect a instrument, for example, this instrument, then I connect this voltage source to this instrument, and the input now if I connect like this, there will be a current flowing in this, the current I that is actually flowing in this. So, this is any instrument, take any instrument whose we want to find out what is input resistance offered by this instrument. So, we want to find what is the input resistance offered. Now, in this case, if you want to find out, then normally what is done is we have the input voltage Vi, then the effective input resistance would be actually Vi by I is what it is given. For example, if I have 1 volt and then if I have, for example, 1 microampere current, then we will have 1 megohm as an input resistance, that is input resistance offered by the instrument is 1 megohm. Basically, we find the voltage and then the current that is flowing, and from there we try to find what is the input resistance offered by the instrument. Now, the input resistance of no consequence as long as the source impedance is 0. So, as long as source impedance is 0, the input resistance offered by the instrument is of no importance. This is because as long as no resistance on the input here, for example, this source has no input resistance. So, whatever may be the current that is flowing, the voltage that is appearing across this is same as Vi. So, the input resistance of the instrument, whether it is low or high, is of no consequence as long as the source resistance is low. Now, the problem comes only when the source resistance is high. For example, if I have a source and which has already internal resistance, it has own internal resistance. Then if I have an instrument that is connected to this, then the input resistance Ri and this is internal resistance Re. So, if we have this, now in this arrangement that Re is the internal resistance of the source. Now, because of Ri, there will be a current in the circuit and that will drop a voltage across this, and if this resistance is lower, that input resistance offered by the instrument is lower, then more current actually flows through this. Now, when more current flows through this, then more voltage drop will occur across this. That means, we will get only less voltage across this, that eventually that the input resistance offered by the instrument matters very much when RE is more, because otherwise it will be a lot of voltage loss. For example, if I take a pH meter, then we have, for example, 100 megohm is the internal resistance of the pH probe. For pH probe, internal resistance is 100 ohm, 100 megohm. Now, even if RA is 100 megohm, even RA is 100 megohm, then only half the voltage will appear, even if RA is equal to 100 ohm, 100 megohm, then half of VI alone appear as input at the instrument. So, but this in this example that we have found that this 100 megohm, because of this 100 megohm and this also 100 megohm, half of the voltage is lost here, only half is appearing here. So, of course, in this case the input resistance is always found by what is the applied voltage across the divided by current that is flowing through that. So, if the input resistance must be higher, if my source impedance is higher, then only it is of then only you can get the entire voltage of the source appearing at the instrument. That is why we like to have the instrument with the as high impedance as possible if you are measuring the voltage. So, ideally speaking, input resistance must be infinite for voltage measurement. That means, if I take a operation amplifier and then operation amplifier sees the input voltage in any instrument, then we have to worry about what is the input resistance offered by the instrument, because if we take any voltage measuring instrument, then we have at the input the operation amplifier appearing, and then we are connecting the operation amplifier to the source, and which has its own internal resistance. Now, the question is, what is the input resistance offered by the operation amplifier? So, what is the input resistance by the op amp? The second question is it always constant? Because theoretically for ideal op amp the input resistance is infinity, but it is not infinity for the ideal op amp. So, second one is for ideal op amp, it is infinite, but for real op amp, it is not infinite. Not only that, it also varies with gain. So, these are two important points we have to realize, that for the real op amp it is not infinite and it varies with the gain, and this is overlooked by most of the designers in real life. This has very big effect in actual error calculation actually. So, we will see how the input impedance looks like if you look at the real op amp, because if we look at the real op amp, what really happens is that we have a input per real op amp. If we take a real op amp, and the input stage consists of the difference amplifier, because we can go back to our original circuit, our operation amplifier design, and see how that it looks like. And then this for example, if you have plus 15 and minus 15, and this is plus input, and this is a minus input, and then this is the output that we have. For example, for voltage follower we are connecting this. Now, we are giving the input here with respect to ground. Now, if you see this, as you increase the voltage, the two things, that is, as you increase this Vi, you will find that the current in this is increasing, and then that is the if I increase this voltage Vi, you will find that the current in this is slightly increasing, and then you find that this current is slightly decreasing, because most of the op amp they maintain this current almost constant, which makes that if I increase the voltage, this current will be increasing and this current will be slightly decreasing. And also we have to realize, even if Vi is 0, even Vi is 0, there is always some current flowing through this. There also there is a current in this. That means this is slightly different from the classical example we had shown with the passive circuits for input resistance. That means, in case of op amp, in case of op amp, even for Vi is equal to 0, there is a current. That means, if I make if I assume this is operation amplifier based instrument, then if I have a resistance here, and even Vi is equal to 0, you will find there is a current I. Even for so there is a current actually flows through this, which is not the case even when Vi is equal to 0. So, here even for Vi is equal to 0, there is a current, current to the input. So, that means this is taken as bias current. So, we are not considering bias current for calculating the input resistance. So, for bias current is not considered, directly for input resistance calculation. Input resistance calculation. However, when the voltage goes up, when the input voltage goes up, bias current increases. This increase in current is due to input resistance. That is how we are taking it. Actually, the increase in current, now we will be taking it as a effective to the input resistance. So, at present that we assume there is no bias current. So, ideally if you want to represent the input resistance in the case of op amp, then I will put like this. So, how to represent the input resistance then? How to represent the input resistance in the op amp. Now, that actually we can represent it in the following way. What you can do is that you have plus minus and you have the input source, then there is a current from plus to minus. We will take this whatever current, when the voltage is increased here, when the voltage is increased, the current is increased, and that current actually increases the current flowing through this. So, keeping that bias current constant, then the extra current can be taken as flowing through this. So, this is considered as RID, equivalent of RID. These are the two gain setting resistors, RF and R1. So, RF and R1 as a gain setting resistance, and RID is taken as a equivalent input resistance. So, RID is called differential input resistance. Differential input resistance of the op amp. So, the increase in voltage, essentially increase in voltage here, the input voltage increase actually increases the current, and that current actually flows through RID. So, but RID is not the input resistance, it is a differential input resistance, that is the resistance that is present between the plus and minus input. So, now I have to find out what is the equivalent input resistance. RID is not the input resistance, it is called a differential input resistance. That is the resistance present between plus and minus, equivalent to plus and minus. So, RID, that means RID is not input resistance. This is called a differential input resistance. This is not the input resistance present at the input, because if I had to convert into equivalent input resistance, then I had to split this RID effectively to the ground side actually. So, what is the current that is flowing through RID, I have to find out, then only I will be able to find the input resistance. So, this actually we can determine by assuming current I in RID. So, we can do this. So, how to find the input resistance? So, we can do in the following manner. What we can do is that we taking this circuit, assume this has some internal resistance and RID. RF by RI, this is RE, and this is the output. So, assuming current I is flowing here. So, voltage let current through RID is I. Then voltage across RID comes RID into I. So, that is the voltage that you get across this, and that is nothing but the difference between plus and minus. So, that means RID into I is the difference between these two, is the differential voltage at the input, differential voltage at the input. So, RID, that means RID into I into A would be equal to output voltage, that is where A is open loop gain, where A is open loop gain, loop gain, and V0 is output voltage. So, essentially what you have done is this RID into I is the input voltage, multiplied by open loop gain is the output voltage equal to V0. So, we have got now the RID I into A equal to V0. Now, we also have to now find out what is the I comes out, that is, if I write for the value for I, then I is nothing but Vi is the input voltage, and then I will take R as the equivalent input resistance. So, then we can write the value of I would be, I is actually we can write it as Vi divided by R, where Vi is the input voltage, R is the input resistance that we are looking for, input resistance. So, if I substitute that in the equation here, suppose if I take this, we substitute for I here, then this will appear like this, that you have RID, because we have one the input is, so I will substitute in equation 1 for I. So, that will come Vi by R, that actually A, that appears to be V naught. Now, I can bring out the V naught at the other side. Now, from this equation I can rearrange, then you will get back RID is the input resistance divided by R into A, that comes out to be V0 Vi. This is nothing but the gain, that V0 Vi is nothing but the gain, but V0 by Vi is nothing but the gain. That actually comes out, that means you will get RID into A by R actually comes out to be G. So, if I can shift the other way around, then I will get that G is, or the input resistance R that what we wanted, then appears to be RID into A divided by G. That means now input resistance now appearing in terms of RID differential resistance and the open loop gain, and then the closed loop gain G. So, G is a closed loop gain. I will write it, G is a closed loop gain. That means input resistance offered by the op amp, which is R actually depends on the closed loop gain that we have set. So, for example, if I give very high gain, then my input resistance will be low. For example, if the open loop gain is 20,000, if I give G also say G 10,000, then this is 20,000, this is G 10,000, then you get 2, then closed loop the input resistance will be RID into 2 only. Whereas, if I keep G as 1, then I will get input resistance very high. So, essentially it means the input resistance, so the input resistance offered by the op amp varies with gain G. Higher the gain, lower the input resistance G. Higher the closed loop gain, here the closed loop gain, lower the input resistance. Now, this is to be realized because if you try to get, for example, take figure of 741 for example, for 741 op amp. If you look at the data sheet, RID is given as 200K. Now, open loop gain A is says minimum of 20,000 is minimum. Then suppose for this case, if I put gain 10 for G is equal to 10, suppose if I put gain of 10 and use non-inverting amplifier like this, that is if I put here 9K and 1K, that means gain 10. Then what is the input resistance offered by the 741? Then what is the input resistance offered by this circuit? If I calculate that, that comes that R will be RID into A by G, that comes 200K and A is 20,000 and G in this case is 10. That comes to be 200 into 10 power 3 into 2000, actually 2 into 10 power 3, that comes 2000 into 10 power 6, that is 2000 megohms. In that case, input resistance offered by the op amp is 2000 megohm, not infinity which normally we think of. Similarly, for example, if I put gain as 1000 for G is equal to 1000, then R comes out to be 200K into 20,000 divided by 1000, which works out to be 200 into 10 power 3 into 20. This works out to be 4 into 10 power 6, that is 4 megohm. So, if I have 1000 gain, then input resistance have come down to 4 megohm, whereas if the gain was 10, the input resistance was 2000 megohm. So, that shows that if we want a high input impedance, then I had give as low gain as possible. For example, the best case would be if for voltage follower, where the gain is 1 follower, then R comes out to be that if we take G into A, that comes 200K the RID into 20,000 divided by 1, that comes 4 into 6, 4 into 10 power 9, or that is equal to 4000 megohms. So, that means voltage follower is the one which gives highest input resistance. So, voltage follower gives highest input resistance. Highest input resistance. That is why when you are dealing with, for example, pH probe, then it is better to have unity gain at the input stage. So, voltage follower if I give, so if it is for example 100 meg ohm internal resistance, then the circuit gives in this case 4000 meg ohm resistance here, equivalent resistance telling is 4000 meg ohm. So, the input resistance that is appearing that is given by this circuit is equal to 4000 meg ohm if I give a unity gain. If I use gain here in this stage, then the input resistance would have come down, and then most of the voltage would have been lost on the internal resistance, because when the internal resistance is high, we have to keep this resistance very high. For that purpose only we have to go for voltage follower at the input stage. Now, you may wonder that what happened to the bias current, is that also to be considered, or we have to consider only the input resistance. In fact, when you are using with the op amp, we also have to consider the bias current error in addition to the input resistance error. For example, if I take the case of pH probe, where we have 100 meg ohm resistance here, and then we are giving this to the input. Assume I have put a voltage follower, and I know that we have 4000 meg ohm here. Whether this 4000 meg ohm present or not, or whether this Vi is here present or not, there is a bias current flowing here Ib. So, that bias current that is flowing through this, the bias current that is actually flowing through this will actually will drop a voltage. Then there is a current that is flowing through this, that current also added to this. So, totally Ib plus this current is what actually flows through this. So, one have to consider for the voltage loss both the cases. For example, here if it is for example, if Ib, the bias current, is equal to 1 picoamps for FET input op amps, for FET input op amp, because you will have very low bias current. So, in this case, for example, we have to use a FET input op amp, maybe it is a 1 picoampere, assume they have taken 1 picoampere, or even we can take say 10 picoampere. In that case, voltage drop on the internal resistance that is equal to 10 power 8 into picoampere is 10 power minus 12. So, we will have okay, we have 10 power 8 into voltage of 10 power 8 into 10 into 10 power minus 12, that comes out to be 10 power 9 into 10 power minus 12, that is equal to 1 millivolt. So, due to the voltage drop on the internal resistance, due to the bias current is 1 millivolt, because we have taken Ib as 10 picoampere. So, you have a loss of voltage 1 millivolt due to bias current. Then in addition to this, there will be a loss of voltage due to the sharing of the due to the input resistance, which is 4000 meg ohm. So, voltage loss, so we can write it voltage loss due to bias current is equal to 1 millivolt. Now, we will find out voltage loss due to input resistance of the op amp. that would be that is actually V I into what is the voltage across the 100 megohm in case of 4000 plus that is the voltage megohm. So, that is the voltage across 100 megohm, because we have this 100 megohm the VI is shared between 100 megohm and this 4000 megohm. So, we want to find out what is the voltage drop across say we want to find out what is the voltage drop across this 100 megohm per VI, because VI is now shared between this 100 megohm and this 4000 megohm. So, that will be that is given by this. So, here in this case it will work out to be that is actually V I into 100. I assume that that will work out to be V I into 1 by 41 it comes. So, if this will be, for example, if it is if V I is equal to say 100 millivolt, then voltage loss equal to 100 divided by 41, that is roughly 2.5 millivolt. So, if the pH probe output is 100 millivolt, then 2.5 millivolt is lost due to the input resistance effect, and then 1 millivolt is lost due to bias current. So, for 100 millivolt pH output, pH probe output, 1 millivolt is lost due to bias current, and 2.5 millivolt is lost due to input resistance, due to input resistance. So, total loss in voltage is equal to bias current loss plus input resistance loss. So, this must be understood clearly in order to calculate the loss at the internal resistance due to bias current and the input resistance. There is one more issue in the input resistance, because there is a package resistance that is there always in addition to the current that is flowing into the circuit terminals of the op amp. So, we have to consider what is the package resistance loss. So, input resistance is also affected by package resistance. That is, if I take if I draw the equivalent circuit, it looks like this, that you have a the input voltage with its internal resistance, then we have here, and we have this is RID into A by G, that is this. Then there is a package resistance which is called RIC, that is common resistance. This resistance is coming due to package. So, effective but package resistance is constant, it is not changing with package resistance is constant. It is not changing, with gain, etc. So, the effective input resistance is in a way. So, for the effective input resistance is the effective input resistance op-amp is RIC parallel R, or other way around, where R is the input resistance, or R is equal to RID into A by G. So, for example, in case of 741 unity gain, for 741 for G is equal to 1, R actually 4000 meg ohm. RIC is also 4000 meg ohm. So, for highest input resistance would be, so for 741 op amp, the best highest input resistance will be 4000 meg ohm, parallel 4000 meg ohm, that comes to be 2000 meg ohm. Then if you have a unity gain, then you can get around effectively 2000 meg ohm as a input resistance. So, one have to worry about the input resistance, and then coupled with the bias current, what is the loss that is taking place at the internal resistance of the source must be calculated in every circuit, and invariably this effect is actually neglected by many of the users. This is wrong, particularly if the gain setting is very high, then input resistance can be very low. So, one should not consider that input resistance is infinite for the op amp and then neglect the effect of input resistance totally. And similarly, the bias current also should not be neglected. Sometimes bias current effect can also be a dramatically very high. For example, we will take one more example to illustrate this. Example 2. In this case, we will show that we have a source, for example, we have a thermocouple voltage is there, and then to protect the thermocouple from short circuit and so on, and we are high voltage coming from this, we added, say for example, 100 meg ohm resistance was added, so 100 kilo ohm was added, and then I connect this one to the operation amplifier, and then I put this, then I have some gain here for say 25 gain I had set here, and then I try to use say some general purpose op amp, and then find out what is the error due to this. For example, if the gain is say 25, then input resistance would be, in this case, input resistance in this case would be, for example, 200k into for example, if it is 25,000 is there, the open loop gain, and then I have 25 gain here, that will come 200 meg ohm. Input resistance will come as a 200 meg ohm. Now, that means it is equivalent telling I have a 200 meg ohm resistance here. Now, if I have 100 kilo ohm resistance, then voltage drop due to the internal resistance, the internal resistance is equal to 100 kilo ohms. So, voltage, assume that this is only 40 millivolts signal, that is what maximum that is expected. So, if I have then voltage drop loss, voltage loss due to internal input resistance. Input resistance would be $40 millivolt into 100 divided by kilo ohms, that is 100 kilo ohms divided by 200 mega ohms. So, that actually works out to be 40 actually into 100 millivolt, and this get cancelled, and then you have 200 into 10 power 6, that works out to be 440 divided by 2 into 10 power minus 6, that comes 20 microvolt. So, we have lost due to internal resistance only 20 microvolt. Now, loss due to bias current. Now, that would be R internal resistance into IB. In this case 100 kilo ohm 10 power 3 into IB. For example, if I use a general purpose op amp, it will be in nanoamps. So, that will be 10 power minus 8, 10 nanoamps. So, IB is taken as 10 nanoamps. That works out to be 100 into 10 power minus 5, that comes to 1 millivolt. See, in this case we have lost more due to bias current than because what we have lost is only 20 millivolt due to input resistance, and we have lost 1 millivolt due to bias current. So, in this case loss due to bias current is more than input resistance loss. So, in that case when I had to go for low bias current op amp than the high input resistance op amp, because that will then only it will make sense, because in this case that resistance what you had used is 100 kilo ohm, for protection purpose we had used 100 kilo ohm. So, that will drop too much voltage due to the bias current. Of course, one may wonder that is that loss is only the bias current loss, is it to be only subtracted or is it can be added also. Actually, the bias current loss, current direction, depends on the op amp. This is a big surprise, because for example, if I take 741, in that case if I take plus minus, the bias current actually goes inside. For 741 bias current actually flows inside. For example, if I take the resistance here, then the bias current actually goes in. Bias current flows from ground to input terminals. For example, this is you take for example another op amp which is say LM324. In this case bias current flows out. This IB, here bias current flows from input to ground. from input. This is because that in 741 if you look at the input stage. So, if you look at the input stage, there actually you have look at this, you basically NPN transistor. So, current is flowing here. So, NPN transistors, here NPN transistors. So, bias current flows here. In the case of LM324, it is actually there is the PNP transistors which are used. In their case, bias current flows out. In this case, here PNP transistor used. So, bias current flows out. In general, most of the op amps actually, most of the op amps are NPN type. So, bias current flows into the terminal, Second one is only generally only rail to rail op amps or single supply op amps. Only single supply op amps use PNP transistors. Or they are called rail to rail op amps. That is, input and output can go up to the supply voltage, and most of them will be single supply op amps. In this case, they use NPN transistor. In that case, current will be flowing out. So, one has to be careful in adding or subtracting the error. For example, if I use LM324 and then use this, you will find, for example, I use LM324, connect this. In this case, bias current will be flowing like this. So, you will have voltage at this point, input voltage would be, you have R I here, and then voltage drop across R I, voltage drop R E, sorry, voltage drop across the internal resistance. Internal resistance R E would be equal to R E into I B. For example, in this case, if I take R E as 100 K, then it is 10 power 5 into 10 nano, that will be 10 power minus 3 volt, that is equal to 1 millivolt. So, you will have 1 millivolt drop across this. Now, this 1 millivolt, suppose if this is a 10 millivolt source, then this 1 millivolt goes through this, that means this is actually plus and then this is minus. So, it is now added to the input source. So, the net input voltage, this voltage is added to the input source. So, the net input voltage, net effective voltage seen by the op amp op amp is equal to 10 millivolt plus 1 millivolt. So, you see this compared to 741, this is totally different case. If it had been a 741, this is for LM324, that is PNP type is used, where the bias current is flowing out for 324 op amp. If it had been 741, in case of 741 op amp, net voltage, the effective voltage at the input of the op amp, input of the op amp would be 10 millivolt minus 1 millivolt, that is 9 millivolt. So, one has to aware of this difference when you are using op amp, whether you are using NPN type or PNP type in calculating the error. In addition to this, that you will have the voltage drop error due to the input resistance. So, in addition to this voltage loss due to input resistance must be calculated as before, which is same for both the cases. There is no difference between the two types for the loss due to input resistance. This error is same for both the types of op amp. There is no difference. So, one can understand that the input resistance and then the bias current complicates the matter quite a lot in the use of operation amplifier. So, one had to be very careful in calculating the input resistance. So, if you want a high input resistance, go for lower gain. So, if you give a lower gain, then you will get a very high resistance. The best is go for voltage follower. If you increase the closed loop gain more and more, the input resistance will keep coming down. That is not actually what is required. So, you should not assume that input resistance of the op amp is infinite all cases and then ignore the effect of the input resistance. That is not correct. So, always worry about this input resistance effect and then be successful in your circuit design. Thank you.